Khovanov homology.
Thank you very much for the introduction. And thank you for having me. It's a great honor to be here and give this talk. So this talk will consist of 3 or 4 different sections, which will be independent of each other. So even if we start with middle of the talk, hopefully it'll all still make sense. So let's start by stating the main result. Oh, and please feel free to interrupt me for questions, comments, clarifications, and so on. Let K be a knot in S3. Then there exists a spectral sequence over F2, the field with 2 elements, that converges to the hat version of not-Floer homology, and whose E2 page is the reduced Khovanov homology of the mirror of the knot. There are a few reasons why this is interesting. First, the existence of such a spectral sequence directly implies that the rank of unreduced Khovanov homology is greater than or equal to the rank of not-Floer homology, which was a conjecture by Rasmussen. And this was proven over the rational coefficients by Dowlin. But my understanding is that dividing by 2 is necessary in the argument. So his argument doesn't work for fields with characteristic 2. And throughout this talk, I would like to work over this field with 2 elements. And on a similar note, there is Belyakova, Futira, Robert Wagner's spectral sequence from triply graded Khovanov-Rozansky-Humphrey PT homology to not-Floer homology over Q. Oh, sorry. Oh, sorry. And oh, sorry. And it seems very interesting to compare these spectral sequences because they seem somewhat different, and I'm very curious what the relationships are. One reason why people would be interested in such a spectral sequence or such a rank inequality is that it actually gives you some knot detection results. So by work of Ashfas and Sabo, one can show that if K is a knot that is not the unknot, then the rank of not-Floer homology is at least 2. One could show this, for instance, using that not-Floer homology detects the genus and using the symmetry. And also, one could see that the rank of reduced Khovanov homology and the rank of not-Floer homology for the unknot are both 1. So these 2 facts directly, together with this rank inequality, directly imply that the unknot is the unique knot for which the rank of Khovanov homology is 1. So this gives another proof of that Khovanov homology detects on Nahm, which was originally proven by Khovanov and Rufka. These are all very interesting, but one thing that I personally find very interesting is the method of the proof of this theorem and the spectral sequence itself, because it seems to me that this spectral sequence is an analog of Khovanov-Rufka's spectral sequence, which is defined for links in S3. And similarly, the E2 page is the reduced Khovanov homology of the mirror of the link. And this converges to an instant-on Floer theoretic invariant called singular instant-on Floer homology, or I natural, of the link. And so I'm sort of sweeping something under the rug. So I'm working in the reduced version, so you really have to choose some distinguished point, but I will not write that here. So at this point, one might wonder why I stated my theorem for knots in S3, whereas Khovanov and Rufka's spectral sequence is for links in S3. And this turns out to be a very important point that I will come back to later. But for now, in section 1 of the talk, but for now, I will tell you a spoiler that the main point, a key point of the proof is defining a link invariant that agrees with not Floer homology for knots and behaves like I natural in general. So one remark, and as the title of the talk might suggest, this link invariant is some version of unoriented link Floer homology. And so the actual main theorem is a spectral sequence from the Khovanov homology of the mirror of the link to some version of unoriented link Floer homology. And also, there exists an unreduced version just like how Khovanov and Rufka also defines an unreduced version of the spectral sequence, which is from unreduced Khovanov homology to another invariant called I sharp. And one reason why this strategy is tricky is because although there's a very well-studied generalization of not Floer homology to links called link Floer homology, this does not work. So what do I mean by this? Well, one intuitive way of thinking about this is that in some sense, you would like to prove that theorem by inducting on the number of crossings on some kind of inductive hypothesis. But then, because if you even start with a knot and resolve some crossings, you will end up with some links with at least two link components. So you really need some kind of statement for links in general. In particular, you want a statement you want the link invariant for links with at least two components. But this is not a candidate because if you do a direct computation, then you could show that the rank of link Floer homology of the half link is 4, whereas the rank of reduced Khovanov homology of the half link is 2. So such a spectral sequence cannot exist. Oh, yep.
The thing that you were calling unoriented link Floer homology, is this the invariant you are mentioning in the spoiler?
Yeah, exactly. Sorry. Yeah, thanks for the question. And I sort of ran out of space, but sorry for this word work. Maybe I wanted to mention one other thing, is that it's a conjecture by Khovanov and Rovka that I natural is isomorphic to not Floer homology for knots over Q. So I would like to move on to the outline of the proof. Are there questions so far? Oops.
Similar result is impossible for links. So this is for no.
Yeah, so actually, there is a similar version for the rank inequality. That's a great question. Where the rank inequality has an additional n2 to the L minus 1 factor here, where L is the number of components of the link. And we also actually get this rank inequality from that spectral sequence.
And by rank, you mean the total rank, or can you improve on?
Oh, yeah, sorry. I was not going to mention anything about gradings in the talk, but maybe I'll just write it here quickly. So I haven't thought about the absolute gradings, but the delta grading on Khovanov homology, which is the relative delta grading, which is quantum grading over 2 minus h, corresponds to the delta grading on unoriented link Floer homology, which for not Floer homology is the Maslov grading minus Alexander grading, or I always get confused when I write this, but it's also this, given some convention. And also, we get that the relative quantum grading divided by 2 mod 2 corresponds to the Alexander grading mod 2. And the differential preserves this grading and lowers this grading by 1 in all the pages. Any more questions?
Sorry, so the inequality over Q was also proved by such a spectral sequence?
Yes, so if you replace the ranks by ranks over Q, then such rank inequality is proven by Dowlin as well. That's my understanding.
Yeah, but by a spectral sequence?
Yeah, so in that case, I think it's a bit slightly different for links, but you still get such a rank inequality for links. So I somehow just erased the statement of the result, but when I first started learning about things along these lines, like rank inequalities and spectral sequences, I was fascinated because it seems to give some relationship between two invariants that are defined in very different ways. Khovanov homology is inherently defined in a very combinatorial way, whereas Floer homology was originally defined using Floer theory. And so a rank inequality like that seemed very mysterious, but over the years, there have been various spectral sequences from Khovanov type invariants to Floer type invariants. And perhaps one of the first instances that I know of was proven by Ashfus and Sabo, where they defined for links in S3 a spectral sequence from the Khovanov homology of the mirror of the link to the hat version of Heegaard-Floer homology of the double branch cover of the link. And in fact, they sort of laid out, now there's a general story for computing, for defining a spectral sequence from, let's say, reduced Khovanov homology to some link homology theory. And this is what I want to talk about in section 1 of this talk. So first, I should really clarify what I mean by link homology theory. So the goal here is to be maximally imprecise. But, and okay, let's work maybe in S3 for simplicity's sake. So for a link in S3, my link homology theory would associate to it a chain complex defined over the field with 2 elements. And I use the convention that if a chain complex has a name starting with a C, then its homology is given by replacing C by H. And so now, in an ideal world, such link homology theory would associate to a link cobordism, a chain map between the 2 chain complexes. But let's try to be minimalistic in this talk and only consider specific types of very simple link cobordisms. Oh, but before that, I should have mentioned that this link would probably have extra decorations. So for instance, we work in the reduced theory, so it would probably have some distinguished base point. And maybe further base points if you work in link Floer homology land. And also maybe some kind of orientations and so on. But I'll try to be imprecise. So what are the cobordisms that I want to consider? I will only consider band maps. So a band on a link is an ambient 2-dimensional one handle on L0. So for instance, if L0 looks something like this, then maybe a band sort of looks like this. And we say that this band goes from L0 to L1 if L1 is obtained from L0 by surging along L0. So in this case, if this was L0, then L1 will look something like this, which happens to be dot naught. And so I want my link homology theory to assign to such bands a chain map from the chain complex for L0 to the chain complex of L1. And maybe I'll denote this as B as well by abuse of notations. And also, this band will probably have extra decorations. Oh, sorry. Any questions so far? Oh, that's a great question. So in this case, I want my band, I don't have any restrictions on whether the band is orientable or not. Okay. So I would like to introduce this general story for defining such a spectral sequence. And it is, given a link homology theory, is sort of a three-step process. I want to go through this quickly through the slides, and I will come back to those and explain each step in more detail. So first step is establishing an unoriented skein exact triangle, whatever that is. And then step 2 is showing that the band maps commute. So if you have two bands, then you could attach the first one first and the second one second, or the other way around. And you want to say the composition of these band maps are the same. But you probably don't actually have that, so you probably want to show this up to homotopy. And then you actually have to show some kind of higher commutativity. Well, in some sense, if you do all this, then you will be able to iterate step 1 to get an unoriented cube of resolutions. And then you get a spectral sequence. Now the only remaining thing is identifying the E2 page of this spectral sequence with Khovanov homology. And this happens to be similar, exactly checking that reduced Khovanov homology and the given link homology theory agree for planar links and planar bands. In other words, the links, when the links and the bands lie in an equatorial S2 of S3. So the links are in particular unlinks, and these are exactly the type of things that you see in the cube of resolutions of Khovanov homology. So then you would actually identify the E1 page with the cube of resolutions chain complex for Khovanov homology. Okay, so I would like to explain each step in a bit more detail. But before that, I would like to introduce one more definition. A crossing ball on a link L is an orientation-preserving embedding of a 3-ball. Say this link lies in S3 into S3, such that the link L looks like this inside the 3-ball. So this is really just a crossing of a link diagram for some link diagram. But I want to make this definition because actually step 1 and step 2 work for any link in any three manifolds. And it's helpful maybe to phrase it in this way. So given such a crossing ball on L, we could define the 0 resolution and the 1 resolution, which is given by changing the link inside the 3 ball as follows. And an example of this is as follows. So if this is my link, and we see a crossing ball here, then the 0 resolution is this, and the 1 resolution is this. And a small warning is that this is the opposite convention of Khovanov homology that you might be used to. So yeah, sorry for that. One thing is that given a crossing ball, we see a band between the 0 resolution and the 1 resolution that looks like this. So for instance, here we see a band that goes like this. Any questions so far? So now I could explain what I meant by step 1. So this, in some sense, deals with the case where we have one crossing ball then we could consider the band map for, associated to this band from the 0 resolution to the 1 resolution. And let's consider the mapping cone of the band map. Which we denote like this. And by step 1, what we want in step 1 is showing that this mapping cone is quasi-isomorphic to the chain complex of L. One question here is why I said an unoriented sky exact triangle. Well, one reason is that by homological algebra, we have an exact triangle that involves the homology of L0, the homology of L1, and the homology of the cone of B, the band map, which I denote it as this, ignoring my convention. And if we have step 1, in other words, if this mapping cone is quasi-isomorphic to that, then we have that this is isomorphic to the homology of L. So we have an exact triangle that relates 3 links like this. And in fact, this result gives us a very simple version of the spectral sequence, where we consider this filtration then this filtration gives rise to a spectral sequence that converges to the homology of L, where the E1 page is the direct sum of the homology of L0 and L1, and the differential is given by the band map, the map that the band map induces on homology. Questions before I move on to step 2? Oh, that's a great question. I think in my version, they might actually be homotopy equivalent, but I really haven't thought about it very carefully. But to me, quasi-isomorphism is a bit easier to think about, yeah. Any other questions? So maybe I'll move on to step 2. So step 2 now is sort of running a similar argument as step 1, but when we have n crossing balls, then there are 2 to the n many ways of resolving the crossings. So given an n component vector with entries 0 and 1, we could define the epsilon resolution which is defined as choosing the epsilon I resolution in the ith crossing ball. Now we want to build a chain complex whose underlying module is the direct sum of the underlying modules of the chain complexes for L epsilon. And the differential has components going from the L epsilon vertex to L epsilon prime vertex for epsilon less than or equal to epsilon prime, where by this I mean each of the components satisfy this inequality for all I. Oops, sorry, how many? Oh, sorry, thanks.
There you go.
Thank you. Nope. Such that, so when epsilon equals epsilon prime, then that component will be exactly the differential on epsilon, L epsilon. And if epsilon and epsilon prime are 1 apart, in other words, if exactly one of the components differ, then the corresponding component will be the band map. So let me demonstrate this with a simple example. If n equals 2, and we consider the following link, and the 2 crossing balls, like this, then the chain complex, well, the underlying module of the chain complex will be this direct sum of 4 modules corresponding to L00, L01, L10, and L11, which look like follows. And in this giant chain complex, the differential will be the sum of the differentials in each of these 4 chain complexes and the sum of these band maps, where, for instance, for this edge, we associate the band map for the band that looks like this. For this, we would associate the band that looks like this, and so on. So say we stop here, and then let's ask whether this is actually a chain complex. So let's think about what del squared is. Actually, let's try to focus on the component of del squared from L00 to L11. And this will be the sum of the composition of these two band maps and these two band maps. And so if we have shown that the band maps commute up to homotopy, maybe let's call the homotopy H, then we can add in the homotopy H to the differential, and then we will get del squared equals 0. So for the vertices that are 2 apart, the corresponding components will be the homotopies. And for the vertices that are at least 3 apart, I think I'm going to wave my hands and say that these correspond to higher homotopies. And to be able to add them in so that del squared equals 0, you will have to show some kind of higher commutativity. Okay. So why did we construct this chain complex? Well, having this chain complex itself doesn't really tell us anything. What we really want to show is that this is quasi-isomorphic to the chain complex for L. And one important remark is that showing that quasi-isomorphism follows from using step 1 multiple times. But I probably won't have time to explain this. But once we have this quasi-isomorphism, then we could consider the Q filtration, which looks like this. This Q filtration gives rise to a spectral sequence that converges to the homology of L, whose E1 page is the underlying module is the direct sum of the homologies of these simple resolutions. And the E1 differential is the sum of the maps that the band maps induce on homology. Any questions about step 2? So now I could explain step 3. So here we started with a very particular set of crossing balls. They in particular arose from a link diagram. So if we have a link diagram, then the crossings will give rise to the crossing balls. And the resolutions L epsilon are the complete resolutions in the Khovanov resolutions, which are in particular planar links. And the bands are planar bands. So if my given link homology theory agreed with reduced Khovanov homology for these things, then the E1 page would just be exactly the Khovanov chain complex. Okay, so to recap, oh, oops. Okay, so this was what I wanted to explain, but I probably won't have time. Okay, so these are the 3 steps. But our goal was to build a spectral sequence from reduced Khovanov to Nahm-Floer homology. And to do this, we actually have another step. Which I alluded to earlier, which is defining a link homology theory such that the homology theory agrees with Nahm-Floer homology for knots, and steps 1 through 3 are satisfied, can be worked out. So it's really a 4-step process. And the strategy is sort of, you define a link homology theory and hope that steps 1 through 3 work. But actually, there was some hint of why unoriented link Floer homology would work. It is possible to arrive at this conclusion that unoriented link Floer homology is the right object to consider. But maybe I will explain this at the last maybe 5 minutes of the talk if I have time. Okay. Oh yeah. So I'm claiming that this is precisely unoriented link Floer homology. Oh, so yeah. So maybe before I move on to section 2, I would like to make a small remark. So I said that link Floer homology doesn't work because the rank inequality doesn't work, but it is actually possible. I guess step 3 also sort of is a bit suspicious, but step 1 already fails for link Floer homology. This is because of the example that I just erased. So if we started with the half link, then the resolutions, 2 resolutions, are both the unknot. But the rank of this is 4, and the rank of these are 1. So there cannot exist a skein exact triangle that involves the homology of these 3 things, because 1 plus 1 is less than 4. But so this is a very beautiful story, but on a different note, there exists a beautiful story by Manolescu, who established an unoriented skein exact triangle for sort of pointed links. They involve link Floer homology, but you have to double the ranks for 2 of the links in such a triple. So in this case, you have to double these 2. So they will have rank 2 each. And this was further studied by Baldwin and Levine, and I'm slightly blanking on the year, who iterated this exact triangle and unfortunately discovered that the E2 page is not a link invariant, but they were able to use a twisted coefficient version of this to come up with a spanning tree model of not-Floer homology. And this was further studied by Baldwin, Levine, and Sharkar, where they defined pointed Khovanov homology and conjectured that if you choose a different filtration on the cube of resolutions corresponding to Manolescu's cube of resolutions, then you actually get a spectral sequence from pointed Khovanov homology. So I would like to introduce the definition of unoriented link-Floer homology, which is originally defined by Ashfas, Stipshitz, and Szabo. So let L be an L-component link in S3. This works in any three manifolds. Then if you want to define Heegaard-Floer type invariance, you actually have to put base points on the link. Say put 2 base points, Ci and Wi, on the ith component, Li of L. And now it's kind of standard from now on. You choose a Heegaard diagram for the link. And then you define the Heegaard-Floer chain complex, which I so I will first define the minus version, or the equivariant version, which is a module over F adjoint U. And I will denote this as CF double sharp of L So I'd spend about a minute drawing this symbol. So to define Heegaard-Floer homology groups, you have to choose a coefficient ring over which the chain complex is freely generated by the intersection points of the alpha torus and the beta torus. And you would also have to choose the weights of the variables. And I choose the coefficient ring to be F adjoint U1 to the 1/2 up to UL to the 1/2. And I assign the weight UI to the 1/2 to both ZI and WI. So this is slightly different from the original definition of Ashfas, Stipshitz, and Szabo for links with at least two components. Where their definition, called HFL prime, is, maybe I'll define CFL prime, which is the quotient of that version by identifying all the variables together. So this is defined over a single variable polynomial ring. And they use this invariant to define a Freushoff type invariant for this theory, which gives an unoriented lower bound of the unoriented Floer genus. So I sort of wrote down the actual formulas here, but one thing you could show is that, in fact, multiplication by ui on this chain complex, these are all homotopic to each other. So the homology, which I denote as HF double sharp, is an F adjoint U1 to the 1/2 up to UL to the 1/2 module, but actually we could identify these together. So in particular, it is actually an F adjoint U module in a sort of nice way, where U is identified with all the UIs, which are all the same. In these kind of Floer theories, once you have a minus version, then you also have the hat versions, which are finite dimensional vector spaces. And here we have two. We have the unreduced hat version, which we denote as CF natural, CF sharp. And this is defined by quotienting out this chain complex by U1. And here, because multiplication by UIs are all homotopic, we could have quotiented out by any of the UIs, and the resulting chain complexes will be all quasi-isomorphic to each other. And we could also define the reduced hat version. To define a reduced theory, we would have to choose a distinguished point. And we define the reduced theory to be CF double sharp quotiented out by UI to the 1/2, where P lies in the ith component of the link L. So one quick remark, given this definition, is that we could quickly compare this with the hat version of link Floer homology. And by definition, we have that the hat version is the version that I just erased, quotiented out by all the variables. And in particular, the hat version for knots is exactly the same as the reduced hat version for knots on the nose, which is exactly what you wanted. And I have 5 minutes, so I have to choose between 3 things. One is doing a computation of the Hopf link, and then I would have wanted to tell you that you actually get rank 2. But I guess I've already sort of shown you the slides. So maybe I'll just remark that if you work in the reduced hat version, then the homology of the Hopf link has rank 2, which is exactly what you wanted. And so that's good. But maybe I would like to spend the last 5 minutes talking about a specific case of this spectral sequence. So let's talk about this particular trefoil, and I think it's the right-handed trefoil. But then we could do a computation and show that these are the chain complexes for the reduced hat version and the unreduced hat versions. So in particular, for the reduced hat version, the homology has rank 3. And for the unreduced hat version, the homology has rank 4, which is exactly what you get, for instance, in Khovanov homology over Q. But in Gheehyun-Floer homology land, we don't really have torsion, so to choose sort of coefficient to work with. And so I just realized I haven't stated the theorem. So, sorry, the theorem is that for links in S3, we have a spectral sequence from reduced Khovanov to the reduced hat version of link-Floer homology. And also, actually, there exists spectral sequence in all the other versions, and also a minus version as well, given by the Lie deformation. But one thing to remark is that these are all defined over F2, so it's not as interesting because, for instance, the unreduced version of Khovanov homology is just 2 copies of the reduced version. Well, I claim that maybe this is a feature and not a bug. So if we consider the trefoil, then just because of rank reasons, the reduced version collapses on the E2 page. But if we work with the unreduced version, then the rank is 4 here, and on the E2 page, the rank is 6. So there has to be a differential. And by formal arguments involving the grading, you could show that the differential is this. Okay, this looks very weird, but let's work in the minus version. Actually, because we have mod 2 coefficients, the minus version looks like this. And this sort of singles out one tower in the Khovanov complex. And this has homological filtration degree -2. And the only other spectral sequence that I know that sort of looks like this is Rasmussen's E-1 spectral sequence, for which Bollinger used to define the T invariant as the homological filtration degree of the surviving generator. And this gives an unoriented four-ball genus, just like the corresponding statement for unoriented link-Floer homology. So I could quickly show you the corresponding thing for T25. It lies in filtration degree -4. And so I would like to finish my talk by asking this question to, asking this question. Thank you very much. Yep.
Are they, I mean, so you haven't said anything about gradings, but if you were to say something about gradings, does like U to the 1/2 have Alexander degree 1/2?
That's a great question. So yeah, so that's a very good question. So, so this is a very unfortunate sort of convention for link homology land because At some point, we used uv to denote the sort of z and w variables, but now u equals zw. And so here, u to the 1/2 is actually z, which equals w. So u to the 1/2 has Alexander degree 1, but the Alexander grading only exists as a mod 2 grading. Also, it has homological grading -1. And this should correspond to the base point action in Khovanov homology. So I can't quite show that the corresponding statement for the reduced version, but for the unreduced version and the equivariant version, we have these base point actions that have quantum grading -2, if I'm correct, in Khovanov homology. And you could consider the Khovanov homology as a module over f adjoint the base point things quotiented out by the base point squared equals u. And this spectral sequence is a spectral sequence of that module. So it respects the base point actions. Where in unoriented link Floer homology, the base point actions correspond to multiplication by ui to the 1/2 if the base point is on the ith component. Did that sort of answer the question? So this is sort of a convention thing because in Khovanov homology, you also have the u variables, which are like, they have quantum rating -4. And yeah, so yeah. Yep.
Do you have any actual dependence on the base point that you choose?
That's a great question. So yes. Yeah, so this is very confusing because Khovanov homology over mod 2 coefficients doesn't. But unoriented link Floer homology does. But also, you sort of expect some weird thing to happen because in general, sort of link Floer homology doesn't have torsion. So you sort of expect maybe unoriented link Floer homology to behave the same in mod 2 coefficients and characteristic 0. So maybe in that point of view, it sort of makes sense that, yeah. And yeah.
You only use band, but what do you know about functoriality?
That's a great question.
Do you actually need functoriality for isotropies or unlinks?
Fortunately for unlinks, there are these base point actions, so I could canonically identify using the gradings and these module structure, the homology with any other thing. So yeah, I don't really have to do hard work regarding that. But I don't know, yeah, I don't really have good, intelligent things to say about what I expect regarding the TQFT structure of unoriented link Floer homology.
More classical link Floer homology is, at least with mod 2 coefficients, is
Yes, but so yeah, I don't really know the history very well, but there's Juha's work and also Zemke's work. But my understanding is that at least Zemke's work considers oriented link cobordisms, whereas in my case, I really need sort of non-orientable cobordisms.
Can you put signs and like user story of the city?
That's an.
Do you know if this would be on Khovanov?
That's a great question. I haven't thought about science and Gheehyun theory at all, but I would expect without really any mathematical reason that if it worked out, then it would probably correspond to even Khovanov, just because the instanton versions where that corresponds to even Khovanov. But I don't really have, there's really no comparison in a mathematical sense that I could make about instanton Floer homology and this version. So, but also I have an exact triangle that looks like Deep-Raj-Bhatt's exact triangle, so maybe that says something, but yeah.
good. If any other questions, then
Thank you very much.